Hello, everyone. My name is Bo Zhao. I'm a PhD student from Humboldt University of Berlin, Germany. Today, on behalf of my co-authors, Han, Tan, Hong, and Matthias, I'm going to talk about efficient integration of remote data in event stream processing. Complex event processing continuously evaluates queries over input event streams from different sources and applications. A CEP query defines sequential patterns, value correlation predicates, including aggregation, joins, or user-defined functions among different events. Some predicates may require external data from remote databases. This is usually because of privacy concerns, for instance, data regulations like GDPR, or implementation considerations, for instance, to split the states from the main memory to the disks. The query results are generated as output events to trigger further actions in real world. Query evaluation incurs latency, that is, the time interval between the appearance of the pattern in input stream and the actual time when it is materialized. The primary goal of CEP is low latency processing. This means the query results become less important with increasing latency. The problem of integration of remote data is that it increases the processing latency. This is because when a CEP engine processes the input stream, when it needs a remote data, it initiates a fetch request and stops stream processing. Only after the remote data has been returned from the remote database to the CEP engine, the stream processing continues. So the problem is that the fetch operation blocks stream processing and significantly increase processing latency. Then our research problem is to reduce remote data transmission latency. To this end, intuitively, we can decouple the time point when data is available and the time point when the data is needed. We can either move the time point when remote data is available closer to the time point when remote data is needed. This is called prefetching. Alternatively, we can also move the time point when remote data is needed closer to the time point when it is available. This is called lazy evaluation. To be more specific, prefetching makes predictions about what remote data will be needed in future and prepares it in a local cache beforehand. So in later time, when the CEP engine actually needs that remote data, it can directly fetch it from the local cache instead of remote databases, therefore hide the remote data transmission latency. So the advantage of prefetching is that it is able to completely hide transmission latency. However, the drawback is that the prediction cannot be always accurate. So it may either prefetch the wrong data, or which will waste the cache capacity, or it may fail to fetch the correct data. Lazy evaluation, on the other hand, does not make predictions of fetch requests at all. Instead, it only initiates fetch request when the remote data is needed. However, it does not stop stream processing. Instead, it relaxes the query predicates and postpones the evaluation of remote data only after the remote data has been returned from the remote database. Therefore, the fetch operation and stream processing can run in parallel. So the advantage of lazy evaluation is that the fetch operation is always accurate. However, it will generate extra partial matches because we are relaxing the value predicates, and the extra partial matches will increase the pattern evaluation latency. So there is a trade-off here. To overcome their limitation and combine the strings, we combine both of them and we propose a hybrid fetching. That is, we always perform prefetching. And if the prefetching does not prepare the correct data, we do not stop stream processing, but we perform lazy evaluation. To realize this idea, we propose the EIRES framework that is composed of 3 components. They are utility modeling, remote data fetching, and cache management. The utility modeling provides cost model based on partial matches. And this cost model is used to guide remote data fetching and cache management. That is, the EIRES framework always fetches the data with the highest utility. And when the cache is full, EIRES is always evicting the remote data item with the lowest utility. Now we look at how utility modeling works. For a certain remote data item, the utility modeling considers its urgent utility, that is, the number of current partial matches that need this item. We also consider its future utility, which is the number of future partial matches that will need this item. And because future utility is something in the future and can only be computed in retrospect, we need to estimate it. And this estimation is based on urgent utility and probabilistic models. And then the overall utility is computed based on both urgent utility and future utility. Turning to prefetching, in order to illustrate how it works, we consider the fraud detection in credit card transactions. And the query shows here detected fraudulent credit card transactions. And the details does not matter, but we only need to know that this query needs to evaluate remote data from external databases. And such a query can be evaluated based on the NFA-based execution model. The state transitions of this NFA are guarded by value predicates. And when the CP engine receives an event, it evaluates it against the value predicates. If the value predicates are satisfied, it stores the event in the state buffer and keeps it as a partial match. It repeats such evaluation until the partial match reaches the accepting state, and then it will generate a complete match. And in this NFA model, the state Q3 will need to evaluate remote data. And this remote data is indexed by event T1's user attribute value. And this attribute value is actually derived from state Q2 and state Q1. So there are 2 possible points to initiate prefetching. That is, whenever a new partial match is constructed at state Q2, or whenever a partial match is constructed at state Q1. Fetching from Q1 is able to hide more transmission latency than fetching from Q2. However, the predictions made by Q2 is more accurate than Q1 because Q2 is closer to Q3. To decide the prefetch timing, we consider the recent history of the cache management. And here we maintain the cache miss matrix. Each column is a state that needs remote data, and each row is a possible fetching point. For state Q3, fetching from Q2 and Q1, they both have the cache hit, which means fetching from both Q1 and Q2 is sufficient. Therefore, we choose Q2 to trigger the prefetching. This is because Q2 is closer to Q3 than Q1, and the prediction is more accurate. However, at later time, because of the dynamic of the streams and the changes of the network connections, fetching from Q2 is not sufficient anymore, and there is a cache miss. So we push one state further, and we trigger prefetching from state Q1. This approach works well for remote data whose index is derived from predecessor state's partial matches. However, there is a situation such that the index of remote data is not derived from its predecessor's partial matches. For instance, here at state Q6, it needs the remote data, which is indexed by T3 event organization value. However, this value is only null when the event T3 comes to the CEP engine. Therefore, we need to estimate the arrival time of event T3. To this end, we estimate the event arrival as a Poisson process, and then we can estimate the inter-arrival time for event T3. Based thereon, we set a timer to trigger prefetching. Now we look at lazy evaluation. As explained before, there is a trade-off of generating extra partial matches and the fraction of hidden transmission latency. To balance this trade-off, we need to select certain states to apply lazy evaluation. To this end, we look at the following execution model. And here, the state transition from Q1 to Q2 need remote data, and we select the states Q2, Q3, and Q4 as lazy states to apply lazy evaluation. It works as follows. When an event arrives at state Q1, the state transition needs to evaluate remote data. So the lazy evaluation initiates fetch requests, but it does not stop stream processing. It relaxes the query predicates and postpones the evaluation of remote data. So the state transition happens and a new partial match is constructed at state Q2. And we also observe the changes of the latency. So when apply the lazy evaluation from Q1 to Q2, we see the increase of the latency to evaluate partial matches, and we see the decrease of data transmission latency, and then the overall latency is reduced compared to the baseline. So we repeatedly apply the lazy evaluation from state transition from Q2 to Q3 and from Q3 to Q4. Now at state Q4, if we still apply lazy evaluation, then we see that the latency to evaluate partial matches suddenly increase a lot. Even though the data transmission latency does not increase, then the overall latency has already succeeded the baseline approaches, and we should avoid this situation. So at the state Q4, we don't apply lazy evaluation anymore. Instead, we block the stream processing and wait for remote data to return. After the remote data has been returned to the local cache, we evaluated it and continues with stream processing. And the extra partial matches processing latency L plus and the hidden transmission latency L minus can only be known in retrospect, and then we need to estimate it. And the hidden transmission latency L minus is actually the time interval for a partial match involved from state Q2 to state Q4. And the extra partial match processing latency L plus is a latency per match multiplied by the number of extra partial matches during this time interval. So the number of extra partial matches can be estimated by a probabilistic models based on the state transitions and the number of current partial matches. And the time interval of IO minus can be estimated again by a compound Poisson process, that is the inter-arrival time of the partial match involvement from Q2 to Q4. Now coming to cache management, the cache eviction policy is based on utility modeling. We separate the cache to two separate tiers. Tier 1 only maintains remote data that will certainly be needed in future, and Tier 2 stores the remote data that may be needed in future. And when the cache is full, we always evict the lowest utility data in Tier 2. However, for remote data in Tier 1, after it first accessed, we move it to Tier 2. This is because after the first hit, we are not sure whether this remote data will be certainly needed anymore. Now we look at our evaluations. We consider 2 synthetic datasets, 2 real-world datasets, and 6 queries. We measure the different percentiles of latencies over more than 1 million complete matches. And we compare our approach to 3 baselines. The first baseline, BL1, is a naive integration, which means the fetch operation blocks the stream processing. And the second baseline, BL2, that is to integrate with the local cache. And here we compare the widely used IO cache against our proposed utility-based cache. And the third baseline is to postpone the evaluation of remote data to the last state of the CEP engine. This is actually the laziest evaluation. We implemented a prototype of an automata-based CEP engine written in C++. The code and data are publicly available. All the experiments are run on a NUMA node with 40 cores and 1 terabyte memory running OpenSUSE operating system. Let's first look at the overall effectiveness and efficiency. We compare prefetching, lazy evaluation, and hybrid approach against 3 baseline approaches on the utility-based cache and IO cache. The horizontal axis illustrates the different approaches, and the vertical axis illustrates the latencies. And here we can observe that the hybrid approach consistently outperforms all other approaches. And prefetching and lazy evaluation also outperforms all the baselines. We can also observe that the prefetching performs better in the utility-based cache. This is because the prefetching made predictions based on utility modeling, and the utility cache and the utility-based cache is aware of this cost model. However, the IO cache is not aware of this utility, so even though the prefetching successfully predict the needed data, but the IO cache is not aware of it and may evict it before its use. Now we look at sensitivity analysis of different parameters of the EIRES framework. We first investigate the utility estimation quality. To this end, we inject noises to utility estimation. And here, the horizontal axis illustrates the different ratios of the noise, and the vertical axis illustrates the overall processing latency. And here, we can observe that the prefetching is most sensitive to utility estimation quality. We can observe that the median latency increases rapidly with the increasing noise ratio. This is because the prefetching makes predictions purely based on the utility. And low-quality utility estimation results in inaccurate predictions, which increase the overall processing latency. We also observe that the median latency of lazy evaluation and hybrid approach is rather stable. This is because for lazy evaluation, it does not make any predictions at all. However, we observe that the 75th percentile and 95th percentile of lazy evaluation also increase rapidly. This is because even though lazy evaluation does not make any predictions, but the cache management is still based on utility modeling. Now moving to the impact of the cache sizes. In general, larger cache improves overall performance. Prefetching is the most sensitive to the cache size. Now we look at the impact of remote data transmission latency. We observe that with the increasing remote data transmission latency, the overall processing latency also increases. And again, prefetching is the most sensitive. This is because for higher transmission latency, the penalty for inaccurate predictions is very high. In conclusion, the remote data integration in event stream processing significantly increase processing latency. To overcome this issue, we decouple the fetching operation of the remote data and its actual use in query evaluation. Therefore, we can hide the transmission latency. To realize this idea, we propose the EIRES framework, which combines prefetching, lazy evaluation, and cache management of remote data.